This is exam 4 for fall 25. I have a rod, it's a mass of 2 kilograms and a length of 2 meters. I want to know a couple things. I want to know the net torque that's acting on the bar. Turns out that's going to be quite easy because there's this force has R equal to 0 and this force has theta equal to 180. So both of those provide 0 torque. This torque provides a clockwise torque. So the net torque will be the force times R times sine theta. That's going to be 10 newtons times 1 meter. That's the distance from where the force is applied to the axis of rotation in 1 meter times the sine of 90. You might not have put that on there. And so that's going to be 10 Newton meters. And it is clockwise. I'll just label it as clockwise, or maybe I'd put a negative there. Either one of those would have been correct. And then I want to know the angular speed of the bar. So there are several steps to this. First, I need to know the moment of inertia. This is a bar, so it's 1/12 m b squared. That's 1/12 of the mass, which is 2 kilograms, times b, which is the length of the bar. That's 2 meters squared. See, that 4 goes there and gives me 2/3 kilogram meter squared. And then I find the angular acceleration, which is torque over axis moment of inertia. The net torque was 10 divided by 2/3, that's 30 over 2, which is equal to 15 radians per second squared. And then finally, I want to know the speed of the bar. Omega equals omega naught plus alpha t. Omega naught is 0, so it's just alpha, which is 15 radians per second squared, times t, which is 4 seconds, so that's 60 radians per second. Oh, that wasn't. Yeah, so. And then the second part, I have a solid sphere with a radius of 3 meters and then a hollow sphere with the same dimensions and mass. I want to know the angular momentum of the solid sphere. Let's go ahead and just determine the moments of inertia for both of these. The moment of inertia of a solid sphere is 2/5 mr squared. You can find that on your equation sheet. That's 2/5 of 10 times 3 squared. That right? Yeah, the radius is 3 meters and the mass is 10. So that 5 goes there and gives me 4 times 9. That's 36 kilogram meters squared. And then the moment of inertia of the hollow sphere, I'll call that HS, is 2/3 mr squared. Remember, the hollow sphere has a bigger moment of inertia than the solid sphere, and we can see that here with this fraction, which is bigger than 2/5. So that's 2/3 of 10 times 3 squared again. That 3 takes away one of those 3s, so that's equal to 60 kilogram meters squared. All right, so there's our moments of inertia. In the first part, I just want to know what is the angular momentum of the solid sphere. So L is going to be equal to ISS times omega. That's 36 kilogram meters squared. I already found that. Times the omega for the solid sphere. It looks like it was 3 radians per second. 3 times 36, that's equal to 108. Or we just do 110, keeping 2 sig figs. What's that? Kilogram meters squared per second. And then what is the speed of the two-sphere system? So this 110 kilogram meters squared per second is going to be equal to the angular momentum of the final system. So I start out with the angular momentum of the solid sphere. That's the only thing that's rotating. And so the initial angular momentum, Li, is equal to that. And it has to equal to the final angular momentum, which is going to be the moment of inertia of the solid sphere plus the moment of inertia of the hollow sphere combined, because they engage and then they rotate at the same angular speed. So that's going to be 110 equals 36 plus 60 times omega final. Again, they're coming together and they're rotating at the same rate, so I just add their moments of inertia. So that if I calculate that for omega, I get 1.1 radians per second. That is 110 over 96 is 1.1 radians per second. All right, let's look at number 3 here. Okay, I have a pipe This is equal to 12 meters per second. This is equal to 4 meters squared. This goes down to 2 meters squared. And then this is, well, I want to know what this is for part A, the fluid velocity. So I could probably just say that, hey, my area goes down by a factor of 2. For my V2 then must go up by a factor of 2, so that's 24 meters per second. Or I could say A1V1 equals A2V2. A1 is 4 meters squared. V1 is 12 meters per second. A2 is 2 meters squared. That's equal to 2 meters squared times V2. And I solved that for V2. That's 48 divided by 2. So V2 is equal to 48 divided by 2, which is 24 meters per second, which is what I thought it was in the first place. Because my area decreases, it has to speed up, and it's going to speed up by the same amount that the area decreased. For part B is a little more complicated. I need to know the pressure. First of all, if V goes up, I know that the pressure goes down. That's from Bernoulli's principle. That was one of the takeaways for Bernoulli's principle. So I better get a pressure that's less than this value. So Bernoulli's principle says that P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. That has the total amount of energy per unit volume has to remain constant. And I have most of these values except for the pressure in the narrow section. That P1 is 500,000 pascals plus 1/2. The density of water is 1,000 times V1. What was V1? 12. That's equal to P2. 1,000 times 24 squared. And then if I solve that for P2, I'll leave that to you. I get 284,000 pascals, which indeed is less than 500,000. I could also write this as 2.84 atmospheres. Okay, either one of those would be correct. All right, for part A, I want to know first, which is bigger, the pressure of the argon gas or the atmospheric pressure? It's argon, because the level of the was it mercury is lower on the argon side. That is, this level is lower than this level. So that's the right answer. I need to know this, and also the explanation is important. And then what is the pressure of the argon gas? I know that P is equal to P naught plus rho GH. That's P naught, which is the atmosphere. That's 1 times 10 to the 5th pascals, is plus, I know that this is actually plus or minus, but this has to be plus because this pressure is actually bigger than the pressure due to the atmosphere, so I need a positive right there. The density of mercury is what, 13,600, I think? Yeah, 13,600. That's on your equation sheet. Times 10 times H. H is what I'm looking for. Oh wait, no, I'm looking for the pressure. H is given is 429 millimeters. That's 0.429 millimeters. Move that decimal place 3 spots. And then that gives me the pressure, which is 158,000 pascals. That's the right answer. Or you could express it in atmospheres, 2 sig figs. Oh, it's like 3 sig figs. 1.58 atmospheres. I just move it over 5. I move it over 5 decimal places. All right. Let's look at this. I have a thin hoop that has a mass of 0.5 kilograms, the radius is spinning at that rate. What is the energy of the hoop? Let's first find what is the moment of inertia. For a thin hoop, I know it's mr squared. That's going to be 0.5 kilograms times 1 meter. Oh, not 1 meter. That's the radius. 0.5 times 1 squared. That's equal to 0.5 kilogram meter squared. That's moment of inertia. And then the energy is equal to 1/2 I omega squared. That is 1/2 of 0.5 times omega, which is 10 radians per second squared. That's 1/4 of 100, or 25. Notice here that this hoop is just stationary. It's spinning about like that. But what if also the hoop had a velocity? That is, not that it was just spinning like about its axis, but it was rolling along the road. Then you would have then another component of the kinetic energy that would be 1/2 mv squared. Not for this problem, because it doesn't have a translational motion, but if it did, if it were instead not just spinning but rolling, that would be 1/2 of m, which is 0.5 kilograms. And then I need to determine v. I'll do that up here. V is equal to omega times r. That would be 10 radians per second times 1 meter, or 10 meters per second. So that'd be 10 meters per second squared. All right, so it would actually be another 25 joules. So there's a 25 joules, that is the rotational kinetic energy. And then if it were rolling, this one is not in this problem, but if it were, it would be an additional 25 joules, which would make the answer 50 joules if it were rolling. But it's not in this problem. So if you thought that was the case and you went through this, you would have found that the answer is not available. But then hopefully you come back and realize that this thing isn't rolling. It's just spinning, okay? This object can rotate in the plane of this page. Rank the moments of inertia. So right away, I see that this one has the most mass at the biggest radii. Look, all this mass. So IA seems pretty clear to me that it's the biggest, so that gets rid of these. And then also I see that IA is definitely different than IB, because they just have a different distribution of mass. So it must be that IA is greater than IB is greater than IC, which is equal to ID. And that fits with the way that I understand moments of inertia. But you could pretty easily just recognize this is the biggest and then pick out the right answer from there. Here I want you to find the moment of inertia. I is equal to the sum of mr squared. That is 1 times 1 squared plus 1 times 1 squared plus 4 times 2 squared. That's equal to 1 plus 1 plus 16. That is 18 kilogram meter squared. Merry-go-round has a moment of inertia of 200 kilogram meter squared, and that radius, I just have this merry-go-round, it has a moment of inertia of 200 kilogram meter squared. But then a kid jumps on, he's 1 meter from the axis of rotation, and he adds an additional mr squared to that. So that's 200 plus the mass of the kid, which is 50, times the radius, which is 1 squared, or 250 kilogram meters squared for number 4. What are the SI units for angular momentum? Well, L is equal to I omega. And remember, I is mr squared. So that's kilogram meter squared for I. Sorry, I got that all messed up. I is the basic definition is the sum of mr squared. So kilogram meter squared. And then omega is in radians per second, or just per second, because the radians is just sort of a placeholder. It's not a real unit. So it's kilogram meter squared per second. A is the right answer. Two disks have the same momentum, that is L1 is equal to L2, or I1 omega 1 is equal to I2 omega 2, but disk A has more energy than disk B. Remember, kinetic energy is 1/2 I omega squared. And so if it has more energy, that means that it's going faster. So the reason that disk A has more energy is because it's going faster than disk B, so A is the right answer. We had several questions like that in the concept test. Point you back towards that if you had difficulty with that. All right, 1 kilogram ball is attached to a string that's 2 meters long. And it spins at 4 revolutions per second, and then the string is lengthened. Let's look at the moments of inertia. I initial is mr squared. That's 1 times 2 squared. 1 kilogram times 2 meters squared, that's 4 kilogram meters squared. And then I final, this string is lengthened to 4 meters, so it's 1 kilogram times 4 meters. squared. So that's equal to 16 kilogram meters squared. So I want to know the new angular speed. I know that Li is equal to Lf, I initial omega initial equals I final omega final. I've already found those moments of inertia. That's 4 kilogram meters squared times omega initial, which is 4 revolutions per second. I don't need to worry about the units here, even though they're not SI units, that the units will all work out in the end. Um, then that's 16 kilogram meters squared. It increases by a factor of 4, and I want to know what omega is. And so omega is going to equal 1 revolution per second. Notice here the units. These units would cancel out with those units and just leave me with revolutions per second. So D is the right answer here for number 7. All right, consider a sketch of the human arm. I know that this is just, a few centimeters. The insertion point where the bicep attaches there is just a few centimeters. This angle also is basically 90 degrees, and I want to know what force is required here in order to have a force equal to about 12 pounds here. That would be a big can, by the way, if it's really a can. That's what it looks like, a 12-pound can of soup. Um, I know that it's definitely not A, that I need a bigger force here in order to get that force. I know it's not smaller either, so it's either B or C. Now, it would be B if this moment arm right here, this distance, was what, half the distance of this moment arm, but it's clearly not. That the difference in this moment arm and this moment arm are about a factor of 10 or so, and so it's going to have a really big force there. This is called a class 3 lever, by the way. I require a big force in my bicep in order to lift that relatively small can. Look, this is a class 1 lever, but with the fulcrums at different points, the axes of rotation. Look, you don't need to know the classes of levers. It's just if you learn that in middle or high school, maybe that'll help you remember it. I want you to list the 3 levers in order of the force that's required to hold this up. All right, so 2 is the biggest force. I'm going from greatest. 2 is the biggest force because this is the smallest moment arm. Remember, torque is equal to F times R. If R is small, that means F is big. So 2 is the biggest, followed by 1 because it's the next biggest moment arm, or next. Yeah, and then followed by 3. So 2, 1, 3 is the right answer. D is the right answer for number 9. What is the net torque here? Recognize that this doesn't provide any torque. This provides a clockwise or negative torque, and this provides a counterclockwise or positive torque. And so the net torque would be 12 times this distance, which is 1 times sine of 30, negative, plus 25 times 1. So that's negative 6 plus 25, which is 19. So it's 19 Newton meters, and since it came out positive, it is counterclockwise. Here I have this boat with a certain volume. What is the buoyant force acting on it? Assuming it's in water, which I think most boats are, floating in water. The buoyant force is equal to the density times the volume times g. This is a relatively straightforward application of Archimedes' principle. Remember, this is the volume of the object. This is the density of the fluid. So that would be 1,000 kilograms per cubic meter times the volume of the object, which is 12, times g, which is 10, 120,000. So relatively, well, medium-sized boat, medium to largest size boat, the buoyant force is quite large. Okay, so this is a continuity equation. Notice I start out with 4 square meters and I go to 1 square meter, and I have 3 meters per second here. So I can imagine here that I'll have a faster speed by a factor of 4, so it's going to be 12 meters per second. So A is the right answer, but again, you can always use the equation. That's 4 times 3 equals 1 times V2 and solve for V2 is equal to 12. All right, what happens? This goes from 4 to 8 square meters, so it gets bigger. As it gets bigger, I know that V is going to go down. And if V goes down, that means that my pressure goes up. So I'm looking for a decrease in velocity. That's going to get rid of these two. And an increase in the pressure. So A is the right answer. I know it doesn't make intuitive sense that if the speed decreases, the pressure increases, but it is nonetheless an application of Bernoulli's principle, which is based on the conservation of energy in a fluid. Continuity equation says that it is based on the idea of the conservation of matter. And what is the mass of 3,000 milliliters of water? Well, you could just say, I know that a milliliter has a mass of 1 gram. You might just know that. That's just sort of a good number to throw around. And if that's the case, then I know that 3 milliliters of water has 3,000 grams of mass, which would be 3 kilograms. Or I could say that 3,000 milliliters is the same as as uh, is the same as 3,000 cubic centimeters. And then you want to convert that into cubic meters. So if I convert that into cubic meters, I would have 1 meter, 100 centimeters. Cube that, and then that has the equivalent of, make sure I get all this right, 3,000 divided by 100 cubed is 0.003 cubic meters. So that's the volume. And then I also know that the density of water is 1,000 kilograms per cubic meter. And if I wanted to know the mass, I would say that the mass is equal to the density times the volume. That would be 1,000 times 0.003, which is the 3 kilograms. So you have to sort of make this unit conversion, and you have to also know that what the density of water, which is on your equation sheet. But easier if you just know that a milliliter is equivalent to a gram, which, as I said, is, if you've been paying attention, like you should sort of just have that number, in your mind. All right. So I have this hydraulic jack. The area of the right piston is 5 times. So if this is A, this is 5A. And if I put in a force F here, I'm going to get out 20 times the force because I know that F over A is equal to F over A. And since I get 5F over here. So if I have 5 times the area, I get 5 times the force. So I put in a force of 20 newtons, and I get out a force of 100 newtons. Here I have a barometer, and I know that the pressure here is 2 atmospheres. Again, if you've been paying attention, you know that the answer is 20 because the a barometer that's filled with water is has a height of 10 meters. And so a barometer filled with water at 2 atmospheres would have a height of twice that, or 20 meters. But again, I don't have to really know that. I can just say that P is equal to rho times G times H. P here, of course, I'm leaving out the P naught because it's equal to 0. P is equal to 2 times 10 to the 5th pascals. That's converting the 2 atmospheres to pascals, is equal to 1,000 kilograms per cubic meter times 10 times H. So H is equal to 20 meters. Which of these matters are compressible? The only one that's compressible is the gas. And then here, a copper wire has a length of 2 meters. L is equal to, we call this L naught, is equal to 2 meters. Has an area equal to 7.1 times 10 to the minus 6 square meters. And it has a force acting on it of 1960 newtons. I want to know what its increasing length is. F over A, the stress that it experiences, is equal to the Young's modulus times L over L naught, delta L over L naught. And I can find that Young's modulus on your equation sheet for copper. It's 11 times 10 to the 10th. So that's going to be 1960 divided by 7.1 times 10 to the negative 6 equals 11 times 10 to the 10th times delta L. That's what I'm looking for. It's increase in length divided by L, which is 2. And if I solve that for delta L, I find that it's 2.5 times 10 to the minus 3 meters, which is 2.5 millimeters. And then finally, Jen's favorite student, of course, all these are awesome students, but I think y'all are all awesome. Okay, that's the end for chapter or exam 4.